Okay, if you have any questions, you can just put in the chat box. Then we can discuss it. Then yeah, if you have any questions, just feel free to answer. Okay, so yeah, again, my name is Jian Hao. Then I'm USM student and one of the alumni in IPHO. My year is 2021, but then because of COVID, we cannot go that year because yeah, COVID for the whole team. So we don't even have the chance to represent IPHO in online. I mean participate IPHO in online. So yeah, I mean my expertise is not um how to say how do I say my undergrad study is in physics. So if you have any questions like regarding like no need to be the thermodynamics or can be etc. Others also you can ask me in the WhatsApp also can. Then today I will cover about the thermodynamics. Okay, when we talking about the thermodynamics, sometimes we are talking about the statistical mechanics. Okay. By the way, this one, the lecture notes, I will send you guys after I finish editing it. I haven't put some of the details like I wish to cover some of them in the lecture notes. Like I think sorry for that, I don't have much time to put in all of it. Okay. So just to give you guys the idea that how can in these 2 hours you can learn something. Okay. Learn something from me. Okay, then hope this guy can enjoy the class also. Okay, and yeah, some of the example I don't put the answer yet, so I will put in the channels. Later on I will send it. Okay, okay, go back to the thermodynamics. Okay, when we are talking about the thermodynamics, we want to specify the states. Okay, we need to know what are the states that we can measure. Okay, macroscopically. For example, the pressure, volume, and temperature. Okay, this one is, for example, you have a gas law, PVT. Okay, relating the PV, VT, or PT. Okay, three gas law. Then this one we can macroscopically looking at it. So we can measure pressure, volume, and also a temperature. But then this most of the equation you will notice that are empirical formula, which is derived from the experimental. I mean derived from the experiments. When you are asking about like why does it behave like this? Why does a gas when the pressure increase, when the pressure increase, the volume increase, for example. Okay, so these properties, when you are talking about why, then you need the statistical mechanics. Okay, and sometimes you will see the kinetic theories. Okay, to derive some of the formulas. Then that time in that specific session we will use the statistical mechanics to derive it. Okay. So we need to use some of the statistical behavior to derive the macroscopically behavior. Okay. So you can imagine that okay, thermodynamics is a study of the macroscopic behaviors. Then we need to use the statistical mechanics to explain their microscopic behaviors. Okay, it's some of the microscopic behaviors, some of it together, then it will become a thermodynamics. Okay, and there is a field also called thermostatistic, where we study the thermodynamics of the statistical behavior in the particles that related to the thermodynamics. Okay, okay, we have when we are talking about the thermodynamics, we have different laws. And to start with, we will start with a lowest number. So it's a zero law of the thermodynamics. When we are talking about a two system, okay, when we have a two system, A and B. Let's say you do the experiment, okay, you notice that they can okay, they are thermal equilibrium with the another system, let's say C. Okay, you do two type of experiment. Okay, the first one you'll notice that they are in thermal equilibrium with the third one, the system C. Then the law said that, okay, the system between A and B, okay, although it's not connected to each other, but then they are in equilibrium with each other. So basically, this is a definition of a zero law. And with this definition, actually, we can derive the meaning of the temperature. Okay, sometimes you can use the statistical mechanics just to give you a hint. Okay, just to give you an idea. If you're going to statistical mechanics, you can derive the how to say, you can define the temperature with the entropy. Okay, and later on we'll see. But then in this, if we are going to the thermodynamics, solely thermodynamics, we have the zero law to help us to define what is the temperature. Okay, let's say you coming up with, you can go to the reference also. I won't show it at all at here. Okay, these are my reference. Okay, basically they demonstrate how we can come up with the idea of the temperature with the zero law of thermodynamics. Okay, you coming up with the define the state of the equation of the state of some state. Equation of state for some system. Let's say you have a system is in the state of T, P, and V. Let's say the temperature is fixed, P pressure is fixed, and V is fixed. So when two systems, let's say you have a T1, P1, and V1. So these are the let's say you have a function T1, T1, and V1 is expressing their behavior, macroscopic behavior of the system. Okay, let's say a function is equal to 0. Okay, then you put it at the left hand side, all of the terms in the left hand side, so you can write in a function of this way. So you have another system like T2, P2, and V2. Okay, it's another function that describes the this system. Another step, for example, P2, V2. Okay, when two of them are equilibrium each other, then you can get rid of something. Okay, you can get rid of some of the variables, and you will basically end up with the temperature is equal to some function of a function of P and V. Okay, then this function we can define as the temperature. Okay. Basically, it's the idea of how to get the temperature from the zero of thermodynamics. Okay. Zero, this is the essence of the zero. Zero give us the give us the temperature. Okay, and we'll see the first law and also the second law. And basically, you can maybe you heard of the third law also, but third law is quite not as significant as the three laws before. Okay, okay. So we specify our minds into the ideal gas and also the real gas. For the ideal gas, we adapt the assumption that the particles do not interact with each other. For example, they do not repulse each other, like the positive. Let's say the particle have a positive charge for the atoms. I mean, particles they have positive charge, they will repel. Okay, the net charge is not zero. But then this assumption, okay, we adapt the assumption that they do not interact with each other. For example, it doesn't attract to each other. Okay, and we can use the kinetic theory of gas. Oops, this is the one. Okay, we can use the kinetic theory of gas to derive the important formula PV equal to nRT. So I think everyone is familiar with this equation. So the P is just a pressure, volume, okay? Pressure, volume, the number of mole, universal gas constant is also the temperature. Okay, and you just need to notice that the Na, okay, the number of Avogadro times with the Boltzmann constant. Also, this K is a Boltzmann constant here. Okay, is equal to the universal gas constant. So you can have the different form of the ideal gas equation. Okay, and despite their you can use the kinetic theory of gas to derive the formula, you can use the, for example, Boyle's law, PV equal to constant. Okay, Charles' law, V over T is constant, and Gay-Lussac law is the pressure law. Okay, another name is a pressure law, so just a PT constant. Okay. Okay, so this, you combine these three together, you can get the PVT. Okay, it's a constant. Okay. So from here you can derive you can get another way to get the ideal gas equation also. Okay. Okay, so we can go into some of the example. Okay, I'm not sure you guys are familiar with the competitive physics. I think, yeah, I think some of you guys are familiar with it, but then I just get an example from the book. So you can have a look. I mean, you can give a try if you want to. Okay, if you haven't tried before, you can try also. Okay, let me just demonstrate. Okay. Okay, let's say you have a thermally insulated piston. Okay, let's say the piston is something like this. Okay, let me draw the diagram again. A and B. Okay, and you have two regions A and B. Okay, initial configuration of the system is something like this. Initial configuration. Okay, with the ideal gas. Okay, so you need to use the ideal gas equation again. One is 27 Celsius, and another one is okay, so A, wait, and the length 0.4 meter, 0.6 meter. Okay, from this. Okay, the piston being initially stationary, so the temperature of the gas in the region now increase. Okay, to 237 Celsius, while the temperature of the gas in the other region is remain at the 27 Celsius. Okay, initial is 27 Celsius, and the region A is increased to 27 to 22. Okay, find the x, the distance of the piston from the left of the. Okay, let's say you increase the temperature, 27. So this one will remain to be 27. Okay. Find the distance of the piston from the left of end of the container after the system had equilibrium. Okay. So yeah, just to interpret, this is the initial condition. You have two region, and this one is the free to move. Okay, means that no resistance. And this one is another region with an A, B here. So the length will be different. Let's say this one X. And this one is what? So total length is 1 meter, right? So it's 1 minus X. Okay, 1 minus X. Okay. And just now, right, we know that because we are talking about ideal gas equation, so PV nRT, and what is the constant here? Okay, you need to think that what is the constant here. So temperature is changing. Okay, so means that the T is changing, and what is a constant? R is a constant, we know. And this is the same gas. Okay, these are the same gas. Okay, with an ideal gas. So we can just write PV. So number of mole is a constant also in these two cases, initial and final condition. Okay. Let's say the first one is P1. Okay, the first state. Okay, the first state is PVT. PVT, initial condition, and the final condition is P2, V2, and T2. and we can divide it. Okay. So get something like this. P2 V2 equal to T1 T1 T2. Okay. So okay, because this is the same surface area, so okay, let's say this one, the piston is the negligible dimension, so these are the same surface area. So the important things we need to know that this we can cancel out the area here. So volume is just the distance, let's say it's a length, okay, L1A, L2A, so we can cancel out the A here, and we can get something like this. Okay, the first one is 37 Celsius. Okay, change to Kelvin. We need to know that Kelvin and T2. T2 is what? Okay, let's say we only talking about the region of A. Okay, we are looking for A first. Okay, so T2 is 227. Okay, L1 and L2. Initial length is 0.4, and another one is X. Okay. Okay, there are three variables. I mean, three unknowns. Okay, maybe we can look at the B first. I mean, just now it's A, now it's B. Okay, and okay, for the B1, we're also using the same equations. P1 L1 over P2 L2 equal to temperature 1, okay, T1 over T2. Okay, but then okay, for the B region, like the first one is 27, and second one also the final temperature also 27 degrees Celsius. I mean, you T1 over the T2, you just get a 1. I mean, okay, the temperature is the same. And the length, okay, length is what? 0.6 initial length, and final length is 1 minus x. Okay, and here is the concept. Okay, what is the P1 and what is the P2? Okay, when we are talking about the two condition, I mean two different situations, the first one, initial one, and also the final one. Okay, so okay, let's say this one is a P1. Okay, you let the piston to move. Okay, the pressure, there's a pressure exert on the this thing. Another one is the, let's say this one P1, P2. Okay, here's a concept you need to be careful that P1 and P2 is the same pressure. I mean, sorry, P1, okay, for the initial condition, also final condition. P1, P2, okay, is the same. So for the B region, initial is the P1 and the final one is the P2. So basically we can cancel out these two, and you can get an answer for x, okay, by solving the two equations. Yeah. Okay. So to wrap up this question, we have the temperature pressure and also the volume for the state of the two condition, initial condition and also final condition. Okay. For the initial one, we know that their temperature, okay, two of the regions is 27, also 27. And for the final state, okay, if we separate to each other, the two regions, and the temperature for the region A is 227 and the region B is 27 degrees Celsius. Okay. And after if they are in equilibrium, the pressure exert, okay, the pressure exert on the wall. Let's say this one is a wall. Pressure exert on the wall for the left hand side in the region A, and from the right hand side in the region B. Okay, it should be the same. Okay, and for the final one, okay, the pressure from the left hand side also right hand side will be the same. Okay, but then it's the different that the pressure will be different when we change the temperature. Okay, so that's why we are using the P1 and P2 for two cases, initial condition and final condition. And we just let the P1 initial and also final, initial, final, for region A and region B will be the same. Okay, so you get the answer something like 10 or 19. Okay. Okay. Guys, okay. Okay. If you have any question, then just put in the chat. If not, I just continue on. Okay. And for the energy, just now we are talking about the ideal gas and also the real gas. Okay, the real gas I haven't included the section about it. Real gas, basically you can think like when the particles, okay, when the particles attract each other, for example, for the particles that is interact with each other, for example, it can be like attract with each other, then the pressure, not pressure, the ideal gas equation, okay, PV equal to nRT isn't it applied, cannot be applied in the real gas anymore. Okay, so yeah, so the gas law for the free gas law, Boyle's law, Charles law, and also the pressure law will not be applied. Okay. Okay. And moving on, we have the first law of thermodynamics. The first law of the thermodynamics is just a statement of the conservation of energy. Okay. So the important point about that is when you are changing the step one, okay, changing the system from step one to step two. Let's say the step one, step two have the function, have a function that describe it, function of PVT, for example, describe it, and you change the step from 1 to 2, okay, let's say this one is P1, V1, and T1, okay, and you change your state to P2, V2, and T2, okay. So yeah, basically it just means that when you change the isolated system from state 1 to state 2, okay, you do the work, and the work that is required, okay, is independent how the work is performed. What does it mean? Okay, for example, you can imagine that from state 1 to state 2, okay, use this. From state 1 to state 2, you can use the way of let's say you can expand it first, then you let it contract. Okay, you have different way to change the pressure. Let's say you change the pressure to P1 and you go back to P2. Okay, or another case, you can change the pressure to P1 and you change the pressure again to P3 into P4 and go back to P2. Okay, let's say you take another route. So it's another, let's say go to P3. Okay. Okay, let's say you the state also change, difference change. Okay, and you go back to the state 2. Okay. It means that this net, okay, this net work done, okay, from initial to the end, right? Okay, it's independent. Okay, it's independent of how the work is performed. So these are the first law. Okay, and if we write it in the mathematical way, it will be du equal to dq plus dw. Okay, sometimes the dw is negative. Depends on how you define the work done. Okay, so here the w is the net work done on the system. Okay, work done on the system. Okay, so you can imagine that from the energy conservation of energy, you have a system. Let's say you have a system here. Okay, you supply the energy. You supply energy as the let's say you supply the energy as the form of Q. Okay, you hit the system, for example. Okay, so you supply the system through the heat. Let's say this one is dq. Okay, and maybe the system will expand. Okay, if the system expand, okay, you do some work done on the system. Okay, at the same time, okay, at the same time, you also increase the internal energy of a system, for example, du. Okay, and yeah, basically, if you write it as the form of dq, you supply it as the du. Okay, with dw. Okay, and this one is a negative here. When we are giving it energy, the work done, okay, the work done will expand by the system. Sorry, the work done will expand by the system. Okay, so I put it as here, so you can means that the amount of energy is supplied into these two ways, increase in internal energy and also the work done by the system. Okay, so you're moving to the sorry, work done by the system. So it should be plus. Okay, so here you get the TU minus CW if the case this one is the by the system. Okay, it should be plus. If you change the sign, if you want to change the sign, you define the work done as on the system. Okay, so this one become plus. You should notice a sign here. Okay. Yeah, conservation of energy. And okay, notice that if we want to see it microscopically, the molecules can gain the energy, okay, can gain the kinetic energy. Okay, can gain the kinetic energy from the translational motion, rotational motion, and also the vibrational motion. Okay, which is depends on the temperature and also the number of atoms or molecules. Okay, let's say you have a the mono atom. Okay? When you have a mono atom, you can gain the energy from three directions: x direction, y direction, and z direction. So you have translational energy from these three directions. When you have more diatomic, okay, diatomic, okay, you need to see that, okay, for example, you have a, I define the direction of x-axis as the this direction, and the y-axis is here, sy, okay, sy and z, okay, z is coming up. So the rotational motion, it only can be from two ways, okay. on two ways because you can rotate the diagram in this way. Okay, but then along the edges, it doesn't it's insignificant. Okay, the rotational motion along the x-axis is not that significant. Okay, so we can only encounter the y direction and also the z direction of the rotational motion. So it depends on. So basically, the rotational motion we have two ways. Okay, translational motion have three ways. Okay, and if you familiar with the degree of freedom, right? Notice that I didn't use a word of degree of freedom because I didn't include it here yet. And I will introduce a degree of freedom in the statistical mechanics words. Okay. Okay, two ways and three ways. And vibrational motion, okay, vibrational motion you can model it as the, let's say, two of them, okay, let's say the monoatomic, sorry, polyatomic. You can model it as a simple harmonic motion. Okay, you attach two of them each other, okay, to a string. Okay, attach two of them with a spring. Okay. So you can use the simple harmonic motion to model the vibrational motion. Okay. Okay. And there is another idea of the heat capacity. Okay, heat capacity depends on the situation. Sometimes the heat capacity it can be the molar heat capacity. Okay, molar heat capacity. Okay, molar heat capacity. And okay, molar heat capacity. And the heat capacity can be the specific heat capacity. When it is a specific capacity, it's just a method. You change the method n to n. Okay, specific capacity. And there is another equation is the Mayer equation. Mayer equations that you can get it from CPCB. Let me show you how we can derive the Mayer equations. Okay. Main equation is just basically you have a relationship between the CV and C heat, constant pressure and constant volume. Okay. Let's say here is the molar heat capacity at the constant pressure and also the constant volume. Okay. And after the summification from du equal to ncv dt, let's say we define from this way, we apply the ncv dt. Okay, right as the dt. And another one is the ncv dt. And we have a first law of thermodynamics. Okay, so first law of thermodynamics is the du dq plus with dw. Okay, and here is the work done on the system. Okay, if this one is the constant pressure, for example, let's say we draw a diagram. We have a piston. Okay, this one is free to move. the cover is free to move, and we have a gas here. Okay, gas, and we okay at a constant pressure means that the pressure is constant. So the pressure is the outside will be balanced by the outside of the atmospheric pressure. Let's say we supply the heat here, Q, okay, Q2. We supply the heat Q2 here, and we can get a Q2. Okay, let me write as dQ2 from Q2. Okay, and initially the piston, the cover is here, and you move in X distance. Okay, means that there is a work done. Okay, there is a work done to expand the gas, the volume. Sorry, you can write S. And part of the energy, heat energy, I mean part of the energy is supply is to increase the internal energy. Okay. So there's another case. Let's say this one is a piston. You fix the cover. So the gas here is the constant volume. Okay, so means that the volume doesn't change, and you provide the heat. Okay, and here is du equal to dq plus dw. Because there is no expand, okay, not expand, so the work done, okay, so won't be the work done here to expand the gas. So here will be du equal to dq. Okay, here is du. I change the du as q1. And here q1 will increase the temperature of dT. Okay. Okay. So if continue with q2 equal to du, and part of the work done is the okay defined as the PdV. Okay, change of volume. Okay, the pressure will be same. Okay, constant P. So this one is equal to okay. Again, we can use the ideal gas equation. So it's PV equal to nRT. Okay, and here is the change in volume. Our P is constant, and nR is the same molar. I mean same mole, and here is the temperature is different. Okay, so the TV here is become dt over P. So our Q2 here is the NCPDT. Okay, so yeah, this one is the, okay, let me write the questions. Q1. For these two equations, how we can link to the above equation, the main equations, Cp equal to Cv plus R. Okay, we have a Cv here, we have a Cp here, and the R is appear and here, it's here only. Okay, how we can get the same one? Okay, if we can think of like for the same amount of gas, right? For the same amount of gas, and if we um increase in the temperature is the same. Okay, for the same amount of gas, and we increase the temperature. Let's say these two are the same gas. If they are we increase their temperature, the internal energy, the increase in internal energy will be the same also. Okay, so actually these two are the same. NCVDT. So we have the NCVDT equal to nRDT times NCPDT. Okay, so these two equations combine. Okay, maybe you need to recall that the internal energy is what? Okay, the internal energy is just a sum of the kinetic energy of the particles plus with the potential energy of the particles. Okay, so you increase their temperature, same increase in temperature, the internal energy will be the same. So you cancel three of them, and dt and dt, and you get a C equal to R minus Cp. Okay. Okay. So yeah, arrange again Cp. CV CDT. Oh, divide. Sorry. Should be NCP minus N1. Okay. Yeah, this one is the main equations. In case you don't know about how the derivation was. Okay. And this one, the monoatomic, diatomic, also the polyatomic. If you link to the how we can talking about how when we talking about the degree of freedom, okay, 3 degree of freedom, 5 degree of freedom, and for the polyatomic, 6 degree of freedom. Okay, okay, yeah, and there are some thermodynamic process that you need to that you didn't know also. Thermodynamic process that okay. Thermodynamic process, for example, you have a adiabatic process. Okay, adiabatic process in the sense that is no heat transfer, or we can say there's adiathermal and reversible. Okay, adiathermal and reversible. PV gamma is a constant. Okay, PV gamma, PV was gamma, PV power of gamma okay, equal to constant, and gamma is a CP over CV here. Okay, and for the isothermal process, is the change of temperature is isothermal. Okay, it's the same temperature. So change of temperature is equal to 0. And you get something of an equation. So just to remind you guys, these two. And the isobaric, okay, isobaric in the sense that the change of pressure is equal to 0. Isochloric or isovolumetric. Okay, isovolumetric, volumetric. Okay, is change of the volume is equal to 0. Okay, sometimes you notice that terms like a diathermal wall, for example, it means that the wall is allowing the heat transfer, okay, between the surrounding and also the object. Okay, I won't derive it here. Okay, PV power gamma and also the labule. Okay, these two equations is easy to get from the books also. I mean, yeah, just this some some part of the process. There are sometimes, yeah, you can get from the books also. Okay, but if we got time at the end of the lecture, I will show you that if we manage to cover all of this. Okay, so just the diabetic, isothermal, isobaric, isochoric, and dithermal. Okay, so this one example I will leave it. Okay, for the heat transfer. Okay, so just now we are talking about the thermodynamic process. Thermodynamic process in the sense that you change a state to another state. Okay, for the same gas, for example, you have a gas, you have equations, you have a function of PVT to describe the gas. Okay, you change this step to another state. This one is the thermodynamic process. Okay, you can through, for example, adiabatic process. Okay, adiabatic process, then you are fixing their no heat transfer. Okay, and also reversible. So it's adiabatic process. And maybe last one you change. Okay, you change their state through the process of the fix their temperature. Okay, so it can be this one the process. Okay, these are the process of the thermodynamic process. Okay? And for the heat transfer, okay, heat transfer is not thermodynamic process, but then you can think like the transfer the heat. Honestly, okay, you can think like, for example, maybe you see the type of it. You can see the type of, for example, convection, conduction, and radiation. Okay, how does you can imagine how we can transfer the heat, okay, from a space to another space. Okay. For example, convection, like, you can think of like the mass movement. Mass movement means that there's a bulk, okay, bulk movement of the fluid particles. Okay, for example, gas and also the liquid. Okay, and for the conduction, vibration, for example, it can be like a solid in a solid or in a metal. Okay, you transfer the heat. Let's say you hit one side. Okay, so you hit one side, so they can transfer the heat through the vibration of the particles. Okay. Okay. And this one is including the movement. Movement means that it cannot be occur in the solid. Okay. I mean, the solid only can be vibrating, right? It cannot be like moved to and move from one side to another side. I mean, the particle from one side to another side. Okay. So conduction, it can be like, I mean, convection, it can be like the liquid and the gas. So here I use the terms of the fluid. Okay, the fluid is including the liquid and gas. Conduction, okay, and also radiation. Radiation means that we can maybe come into your minds like black body radiation, and we will talk about it later also. It is through the electromagnetic wave, in the sense that it doesn't need a medium. Okay, electromagnetic wave doesn't need a medium, and other two is you need to have a medium for it to transfer the heat. Okay. And oops. Okay, and for the convection, okay, convection is change orientation. Okay, okay, convection. One of the law that is important, I mean, there are some assumption. Okay, for example, the temperature difference between them is small. Okay, small temperature difference. We can use the Newton's law of cooling. Okay, and there's a statement about heat flux density. Okay, heat flux density means that net heat flux density. So density is something like divided by the volume or divided by the area, depends on the context. Okay, here is the okay. Okay, here is the volume. Sorry, here is the area. Okay, so the net heat flux density is proportional to the temperature difference between them. So the temperature difference, for example, the temperature of the object and the temperature of the surrounding. Okay, temperature of the object and also the temperature of surrounding. There's a minus sign here is indicating that the temperature is because it's cooling, right? It's moving from the T to the surrounding. Okay, higher temperature, the heat will loss, okay, from the higher temperature to lower temperature, which is surrounding. Okay, maybe you can try an example how we can apply this formula. Okay, let's say we have a cup of coffee. Okay, you have a cup of coffee. Okay, you have a cup of coffee, and this cup of coffee is obeying the Newton law of cooling. Okay, so you have let me say, a cup of coffee. This area is contacting with the surrounding. Okay, and okay, you need to find the instantaneous temperature. Okay, temperature in as a function of T. Okay, and let's say you start with a temperature for T naught. Okay, T naught is the initial temperature, and you let it cool. Okay, the cooling is through, let's say, it's through the convection. Okay, convection to the surrounding only, and you can use the units of cooling. Okay, let me write the equation again. Q dot S T minus T surrounding temperature. Okay, surrounding temperature is A, temperature A. Okay. Okay, how we can do this? Okay. At first, we need to know that this one, okay, the heat transfer process, this one, temperature of a room. Okay, temperature of a room is approximately constant through the heat transfer process. Okay. So from the temperature of T naught to the surrounding temperature is T. Okay. This one is a net heat flux. It's proportional. So we can write as, for example, we write in K, indicate K dot T minus T surrounding temperature. Okay. And we can interpret the net heat flux density as the net power transmitted per unit of the perpendicular area. Okay. Net power transmitted. Okay, net power transmitted. It means that, for example, like the Q here is the, okay, let's say the Q here is the heat, right? Okay, something like the energy. Okay. Power is what? Power is the change of, for example, I use E becomes a Q, dQ over dt here. Okay. So the Q dot here, okay, Q dot here we can write as the Q dot divided by the per unit perpendicular area. So this one is the power transmitted. And so I can write the same T minus TA. Okay. So it's Q dot means KA T minus TA. Yeah, because I need to get a function of the T, right? So I need to solve for T. So it's a T. Yeah, I'm just like T Q prime. Okay, I missed something. Oh yeah, the heat capacity. Okay, the heat capacity it also assume that it's a constant. So this one it doesn't mean that it doesn't tell us like it's a specific or the molar. So I just use the, for example, the Q equal to CT. Okay, you provide a heat. Specific capacity is like you provide the amount of heat required to increase the temperature of the 1 degree of Celsius, for example. Okay, or you need to use, or you want to use the 1 Kelvin or something. Okay, so I use a Q equal to CT, as the C is the heat capacity. It doesn't specify as the mass or molar. Okay, so given the Q equal to CT, and I have the Q dot. Q dot means that is the dq over dt. Okay, Q dot is a power. Okay, or dq over dt. So I differentiate both sides, so become the Q dot CT dot. C is a constant here, so we can ignore it, and it becomes like a CT dot. You take Ka T minus Ta. Okay, so okay, moving on. I can do some integration because it's involving the dt. This one is the d big T over small t. So it's something like dtc, and negative K. I bring the T to the left hand side. T is TA, Ka, dt. Okay, so this one is constant. So this one C is constant. So it's something like differentiate, integrate 1 over T. 1 over T minus TA dt is the log. Okay, we get the log. Okay, this is constant. So it's something like T minus T. Okay, so let's see. Okay, so I put the integration sign from, okay, you're changing the temperature from T naught to certain T. Okay, to certain T. Although sometimes, like, if you very rigorous with maths, we cannot use the same variable here. Why? Because it's the same, right? Sometimes mathematician tends to like change the T to another one, for example, T prime, okay, to express it is different than the dt. Okay, it depends on your favor. Okay, I mean, we are the physicists, so we can just exploit the notation. I mean, exploit. Yeah, we know that it's a function of t. No, it's a function of small t. Okay, so this one becomes the C. This one is t is what, from 0 time to time t, so it's negative k t. Okay, so you substitute the t and t now, it becomes long 1 over t. Okay, okay, here you notice a very weird thing. T substitute into t is the same thing. I mean, yeah, mathematics. T means t minus with long 1 over t, not minus ta. So negative ka t. So something you will get something like limiting, what you will get ckt divide. So you get something like t is equal to negative kat exponent ekt a over c. So c a over c t t minus ta because of t minus ta plus with ta. Okay, change to get this. Okay. So this one will be the instantaneous temperature. Okay, so if you draw the graph, right? Okay, you need to draw the graph, for example, okay, t versus small t. at time t equal to 0, okay, time t equal to 0 is substitute equal to 0. Just need to check is it reasonable. Okay, t equal to 0 is exponent power 0 is 1, so t naught, so you get a t naught. Okay, yeah, you start with a t naught, right? Yeah, it's a good thing. Okay, you know. So and what t naught? T naught is t in. And let's say you can try to substitute some values. Okay, I think you will get something like this one. Okay, this one is exponent, so but it is reverse it. I think it's something like this. So you will approximate the values. Okay, let's say you want to draw a graph. You take the t approach to infinity. Okay, what does it approach? T approach to infinity. So e negative infinity is 0. You know. Okay, again. So you check the graph. Okay. So look at the two extreme. The first case is a t equal to 0 and t equal to approach to infinity. So t approach to infinity. Okay. Exponential graph is something like this. So you take this one is f of t exponential, and if f negative t, okay, I mean if ft is the exponent something, so you take the negative t is just the reflection. So something like this. Okay, this is one. Okay, so when you approach to infinity, your exponent negative something constant with t. Okay, this constant and let it like a constant with t will approach with 0. Okay, so yeah, approach to 0. So this one will approach to 0. So your t will approach to t. Okay, so this is something like you will stop at t. Okay, seems like reasonable because your cup of the sorry, your coffee won't go down below the temperature T8, right? Because your surrounding temperature is T. Okay, even time. Yeah. Okay. Okay. This is a Newton's law of cooling. Okay, in the sense that you can apply it to the change of temperature. Okay, it's very small. Okay, small different temperature difference. Okay, and there's another one for conduction. Okay, this one is convection. Okay, so another one is a conduction. Okay, conduction, if you apply, I mean, if you are familiar with a one-dimensional form, if you are picky, okay, you can write in the three-dimensional form. Okay, it's just the T become a temperature, okay, in the x direction, y direction, x and z direction. So you have three vectors, and you specify your case to become one-dimensional. It becomes q dot. Q dot here is the same. It's a net heat flux, net heat flux density. Okay, basically k dt over dx. This one dt over dx is the temperature gradient. Okay, temperature gradient. Okay, and negative here is means that the flux density points toward the direction of the decreasing temperature. Okay, again you can try on it. Okay, maybe you can skip first this one. Cool. Okay. This one is also you need to apply the integration. Okay, another one is a Stefan-Boltzmann law. Stefan-Boltzmann law, okay, there is some historical issue. It's very interesting because I mean, how to say? it's one of my internship project in university. So I'm doing some investigation on the uh, historical issue, on quantum mechanics. Okay, I mean doing with one of the mathematics professor. So he asking me uh, why we need to have the quantization of the energy in the quantum mechanics. So yeah, I do some of the homework. Okay, so I can tell you some story. Okay, so yeah, historically, if you when we how to say classical physics has some breakout. How to say okay, at that time, right, the classical physics have Newton's law is quite successful. Newton's law and also the electrodynamics. By the Maxwell equations, four equation is quite successful already. So, but then they have some breakthroughs. Okay, I mean, haven't the the questions that doesn't solved by the physicists yet. Okay, one of them is the black body. Okay, black body radiation. Okay, the black body radiation is like is a perfect emitting surface. Okay, and it took some of the time for the people to verify the experimental result because black body come up with the at the first is the experimental result. Okay, experimental result that is that's proving that a body will emit the radiation. Okay, at the first is Stephen Boltzmann, means Stephen. Okay, Stephen is successful to derive the expression to explain the black body behavior, but then it's from the kinetic theory. Okay, um, he also using some of the Boltzmann distribution. Okay, Boltzmann distribution. When we are talking about the kinetic theory, we have Boltzmann distribution. Okay, Boltzmann distribution and apply the Boltzmann constant also. And at the end, okay, at the end, it can prove that the equation is something like P equal to, sorry, this one you can use, you can write as a P. Okay, P equal to sigma AT4 power 4. A is the area of the surface. Okay, and just like I said that dq over dt, right? Dq over dt is a power, so this one is power over A. This one is equal to dot q. Okay, this one, right? Okay, is derived by the Stephen. Okay, and he found there's a constant called the Stephen-Boltzmann constant. Okay, this one is not. He doesn't know that how we can. How does it Stephen-Boltzmann constant link to other constant? I mean, it's quite weird that there's a new constant here. How does it link to the another constant? For example, there's a constant for example, you want to link the Stephen Boltzmann constant to the spring, for example. I mean, I just randomly put some constant, spring or G, okay, gravitational constant or what, okay. So it's not like the more like the empirical driven constant. Okay, so he cannot explain what is the Stephen Boltzmann constant about. Okay, and later some time there's two people. There are two people, Vian and also the Rayleigh twins, three people. So like the black body radiation is something like this. Okay, black body radiation. I mean just a curve. And the curve is like the this one is temperature, not temperature, frequency. Okay. The Wien's law, okay, not the Wien's displacement law. The Wien's law is the general law, okay, general law of the displacement law. Okay. The Wien's law, it can be explained the higher part of the temperature frequency part. So it means that it can successful to explain, okay, this one is can use this equation to explain. Okay. For the lower energy part, sorry, lower frequency part, there is a Rayleigh law. Okay. Rayleigh's law is you can use that to explain, okay, the lower frequency part of the observation of the black body radiation. You can check on it if you are curious what is the Rayleigh's law. Okay, and it took some time. Okay, there's a physicist, okay, called Max Planck. Okay, there's some physicist called Max Planck. It derived the formula for the whole frequency spectrum for the backbody radiation. Okay, imagine that the people have the frequency, have the equation for the higher frequency part and also lower frequency part. They want to combine these two equations. So, okay, but many people fail. Okay, at the end, Max Planck derive it typically and use the idea of the quantization of energy. He used some logic. He used some logic, like for example, okay, let's say he have a formula, okay, well properly defined formula that can explain this spectrum. Then it's trying to use different scenario. Okay, different scenario. For example, for the first one, the option A, I quantize it. I mean, the energy becomes the discrete, and maybe for the option B, the energy is not conserved. Okay, this is not quite true. Okay, so at the end, he found that he need to use the idea of the energy is discrete to explain black body radiation. Okay? So that time he quite furious with the idea of the quantization of energy to explain black body radiation. And at the end, we know that okay, this is the start of the quantum mechanics. Yeah, so yeah, hopefully you can get some of the points in it. Okay. Yeah, just a research thing. Okay, so but then we only focus on the Stephen-Boltzmann law. Okay, Stephen-Boltzmann law, and also we need to know that the emissivity of the body, okay, for the black body is equal to 1, and for the other body is less than 1. Okay, and yeah, you can try to use a kinetic theory. They give you a challenge. You can try to use a kinetic theory to derive the Stephen-Boltzmann law. Okay, kinetic theory is something like you need to apply the uh, if you are familiar with a triple integration, okay, because it's across a volume, right? It's a bread body. Let's say you define it as a spherical body, okay, so it's the triple integral. Okay, uh, I mean IPSO is not including this triple integral or double integral, but then if you have this mathematical skill, right, it's useful for you. I mean, if you are going to engineering, also useful for you also. In the university, also useful for you if I continue in the science stream. Triple integral. Okay. I mean, you go some economics undergrad, you will use this triple integral. Okay, so data history. Something is also the William displacement law. Okay, William displacement law that is just like when you have a peak of the wavelength. Okay, it just B is a constant, so means that you change your temperature. Let's say you increase your temperature, so when you increase your temperature, your wavelength will become lesser. So if you are plotting a graph like is x-axis is a wavelength, okay. Let's say this one is your distribution, like the bread body, or something like this. So your peak here, it will shift to the left, okay, when the temperature is higher. It's just a Williams displacement law. It's just a specific case of the Williams law. Okay. Okay. Moving on, we have some part. Okay. I wish I can give you the idea of the what is the ensemble also. Okay, at the end. Okay, entropy. Just now we have a second law of thermodynamics, first law and zero law. Sorry, first law and zero law. Now we want to look at the second. Okay, second law we have equivalent statements. Okay, different equivalent statements. So equivalent statement means that this 1, 2, 3 are equivalent. Means although they are wording, right? The wording, okay, the wording is different. It's a bit different. I mean, but then at the end, it leads to the concept of the entropy. Okay, actually, it's an equivalent statement that build up the second law of thermodynamics. Okay, so yeah, you can try to think that why they are equivalent. Okay, I mean, It's just something like you have a mathematical theorem. Okay, when you have a mathematical theorem, you have a first statement, second statement, and third statement. Okay, and you say that these three statements are equivalent. Okay, in mathematics, you need to prove that. Like for example, this one y first is leads to 2, 2y leads to 3, 3 leads to 1. So they are the logic. You can y is circular. Yeah, you can 1 to 2, 2 to 1, 3 to 2, 2 to 3. It's something like this, if I'm not mistaken. Okay, so you can think that why they are equivalent in physics. I mean, in this second. Okay, okay. The first segment is like Kelvin, and second is Clausius, and third one is a Carnot. Okay, the first one is like no process is possible where the Hall effect. Okay, the whole Hall effect is the complete conversion of heat into the work. Okay, it means that you have you want to change you have a system. Okay, you want to change the heat. Okay, you want to convert it, all of the heat to the work. Okay, and the Clausius. Clausius is about the no Hall effect, no process where the Hall effect is the transfer of heat from a colder to the hotter body. Okay, Hall effect means that there's a cold body and the hot body. The Hall effect is like every heat transfer is going to here, cold to hot, cold to hot. Okay, it doesn't occurs in this case. Although it sometimes statistically, if it occurs, very low probability that the cold temperature will transfer heat to the hot temperature. But then microscopically, it whole of the process like no process is like whole no process is like whole heat transfer process is transfer the heat from cold to hot. Okay, 就 get my point. Okay. Statistically, it can appear, but very low temperature is seldom appears. Okay. And for the Carnot is like for all the heat engines, like heat engine is like the for example, you're operating the cyclic process. Okay, it's converting the heat to work. Okay. Let's say you have a temperature T1 and so T2. The most efficient one is a Carnot engine. Okay. The Carnot cycle is a kind of engine. Carnot cycle is like you have a let's say you draw the diagram of PV. Okay. You have an isothermal process and two isothermal process and also two adiabatic process. Okay. Let's say there's a PV here, different curve. Okay. Let's say you have a cyclic process. Okay. Let's say this one is your cycle. Okay. So this one is a Carnot cycles where two of them is adiabatic process, another two is isothermal process, fixed temperature and also a no heat transfer process. Okay. Carnot engine is just the engine that you are using. They are using the Carnot cycle. Okay. Okay. And there's another idea is like the efficiency. Okay. When we are talking about the efficiency of an engine, we want to investigate about the energy output over the energy input. Okay. Efficiency is just basically this definition. When you're talking about the electrical things, like electrical components, their efficiency also is like the energy output or power output over power input. Okay, power is linked to the energy. Okay, so this one is the energy output over energy input. Okay, you can think like they have the um, heat in and also the output heat. Okay, you have a reservoir. Reservoir means that you can draw the heat. I mean, you can draw some of the energy from it, but then their temperature is not changing. Okay, so it's hot and cold. You have an engine. Okay, let's say you have an engine. The hot will flow from here, right? Okay. Let's say this one is the input heat, and this one is the output heat. Okay, and the difference of it, right? The difference of it will become the work done. you can imagine that the work done is you can think of like the energy is going for the output energy. Okay, so you minus these two, you become the output energy, kind of like output energy. So you divide it, output energy divided by the input things like input energy. Okay, so you input the hot one, so you become the efficiency. Okay, depends on you want to multiply on 100% or not. Okay, I mean just give you a fraction. Okay, and from the Carnot statement of the second law of thermodynamics, the best one is the Carnot engine. Okay, Carnot engine. This one we can verify it why this one is the best engine. Why Carnot engine is the best engine using the entropy idea. Okay, entropy idea. So yeah, with the entropy equations, just now we have a ds equal to dq over t that we'll see later on, and q is the heat, okay, reversible heat. Okay, I mean just skip to the entropy first. Okay, the increase in entropy of a body, right, at the temperature T, okay, that receive a heat, okay, dq reversible heat is ds equal to dq over t. Okay, if the process is reversible. So this one is the entropy. We can get the entropy from this equation. The S is our entropy. Okay, so yeah. Okay, let's say we have an engine. Efficiency is the again. Okay, we have an engine. Efficiency is like W over Q in. Okay, and W here is Q in minus Q out. Okay, this one is very easy to derive. So this one become like minus Q out over Q in. Okay, and for the Carnot cycle is something like it's a reversible process. Okay, Carnot cycle is a reversible process. Means that if you have a one cycle, right? Let's say you change from the state of let's say you have 4 states. Okay, one cycle is what? You start from state 1, okay, state 1 to state 2, 3, 4, and back to 1. Okay, so it's like one cycle is something like here to here and here, for example. Okay, so you're going back to the original state. Okay, so original state, because it's a reversible process in the sense that you reverse a process, you will get the same state. Okay, and because it's a reversible process, we can use the equation of ds with dq over t. Okay, okay, and okay, and there's another assumption for the Carnot cycle also, Carnot engine. Okay, it won't affect. Okay, let's say you draw the heat from your reservoir, hot reservoir, and give the heat to the cold reservoir just now. Okay, hot and cold. Okay, draw the heat from the hot reservoir and give the heat to the cold reservoir. And there's a Carnot cycle is that you won't affect the reservoir. Reservoir is means that you doesn't change their temperature. Okay, you draw the heat and give the heat. Okay, it's very big amount of the reservoir. It doesn't affect their temperature, so it doesn't change their temperature. So it means that this one is the change of the entropy will become equal to 0. Oh, sorry. In dq over t, dq over t. No, okay. Change of entropy is the same for. I mean, it's the same for two process. One cycle. So, for example, this one temperature 1. Cool. and this one is the, so core is one, core is out. So you substitute the TQ, you get this equation. Okay. And you substitute this one into the efficiency, okay, Carnot engine, and you will get the equation back, 5.1. Okay, this one is second law. In the second law, okay, going to the next one, yeah, we can get it this one. Okay, going to the next one, right, is the entropy. It's linked to the entropy, or there's another principle, postulate. So postulate means that it proposed that for us to build up the some of the principle postulate. You can think of like the postulate is something like the axiom, but it's not quite strong as the axiom in mathematics. But then in mathematics, we didn't use the axiom. I mean, we didn't use the postulate to call in the mathematics field. Postulate is something like in the physics field of the physics. The physics that we are using, the postulate of the first postulate, the second postulate of the quantum mechanics, for example. Okay, so it's something for us to assume that it's true, for us to build up some of the principle, or build up some of the law. Okay, so sometimes we like to interchange with the law and the postulate because it how to say, it's a mathematics. I mean, yeah, just a terms. For it, just a terms. So we will interchange with using that. Okay, you notice that physics is not that strict with as strict as the mathematician. It's like exploit many things. Okay, the entropy. Okay, it's about when your temperature is close to zero, the entropy will become to zero. Okay, so it gives us the baseline. Okay, a baseline to measure the entropy. Okay. Yeah, and just now we are talking about entropy definition, and this one I'm first to cover it just now. I mean, in this section, so I haven't put in yet. I think I can maybe put in later on. Also some of the fun fact. Okay, we have another half an hour, and we will go to the statistical mechanics. Okay, we quite fit, how to say, fast track. We quite go very fast on the thermodynamics and also statistical mechanics things. Okay, into so they have many things that I haven't covered in the thermodynamics. So for example, the thermodynamic circuit. Okay, thermodynamic circuit. Yeah, in details of the law and also example. I didn't go through many questions, and if you can use the books also to find the question to solve up. Okay. Okay, so the next one will be the statistical mechanics. Okay, just now we are talking about statistical mechanics is something like it's a way for us to explain the thermodynamics behaviors in microscopically. Okay, so when we are going to the microscopically, we see on the particle stuff. Okay, if we able to model and simulation and do the simulation on all of the particles. Okay, let's say for one more, right? One more we have a 6.6 something. Okay. This number of particles. Okay. And if you're able to use a computer to simulate, we can get the exact same result as what we see in the experiment, okay, microscopically. But then sometimes we can use the statistical methods to approximate some of the equations, so we can get at least some of the useful result for us. So for example, you can use like the central limit theorem. Okay, it's quite famous in the statistic. Central limit theorem. Okay, and another one, for example, you can use the Boltzmann distribution. Okay, Boltzmann distribution when um, when we are solving a statistical mechanics. Okay, okay, okay. And one of the important theorem that we encounter is the equipartition theorem. It's something like you have uh, the average of the energy, average kinetic energy is equal to half of a kBt. I'm not sure you guys seeing how why does it true for you or not. And then in my time it's like I just accept it, but then this one I trying to explain to you how we can get a kBt over 2 from the statistical mechanics. Okay, so we try to prove this equipartition theorem. Okay, let me see the statement again. Okay, the statement about the equipartition theorem is like when we have an internal energy of a classical system. Classical system means that we don't encounter the quantum system. I mean, we don't take into account the quantum system. Quantum system is something like for example, the vibrational motion. The vibrational motion, you need some of the quantum stuff, right, to explain certain things, to explain the vibrational motion. So you can think like, okay, we only look at the translational, and also the rotational. Okay, two types: translational energy and also translational kinetic energy and rotational kinetic energy. Okay. Let's say we have a large number of the particles in the thermal equilibrium. Okay, if you distribute evenly among each other with of the quadratic degree of freedom, quadratic, okay, degree of freedom, okay, degree of freedom accessible to the particles of the system. Okay, what does it mean? Okay, let's see. Okay, okay, so okay, means that for each degree of freedom, let's say your degree of freedom is equal to 1, and your uh, average kinetic energy is equal to half kBt. kBt. If your degree of freedom is equal to 3, your average kinetic energy is 3 over 2 kBt. It's something that you look saw this before. Okay. And we need some of the tools like the Gaussian integral and also the um what I call Boltzmann distribution. Okay. This one I will include in the notes also. You see. Okay. Let me try to demonstrate for you. Okay. Let's say we have a system of we have the energy of a system is like is equal to some constant times with the one of the variable. The variable can be like the position. It can be the okay. It can be the position. It can be the velocity. For example, half mv squared. This one is what? For the harmonic motion, simple harmonic motion, the potential energy, okay, is linked to is proportional to x squared. And let's say we have half I omega squared is a rotational kinetic energy. Okay, so let's say this one x variable, it can be anything. It can be any variable. Okay, so it's a power square. So the square means that it's a quadratic power. So quadratic degree of freedom. I mean the quadratic here means that this one is a power 2. Let's say you have some constant. This one is constant. Okay, or some variable. Okay, we want to assume also there is one of the postulate of the statistical mechanics. Okay, of the postulate of the statistical mechanics, we want to say that x could be in principle take any values with equal probability. Okay, being reminding you guys again what we are doing. We are doing about the we are doing trying to prove that the mean average kinetic energy of a system for 1 degree of freedom, for example, is half kpt. For n degree of system is this next example, it will be n over 2 kpt. Okay, so let's see about it. So this procedure is helpful for us to express the probability. Okay. Okay. For example, we want to find the average kinetic energy. Right? So average kinetic energy, we just take the average on the square. Okay. If this one is a constant, we can pull it out. Okay, this one is very simple to verify. Okay, I mean these two things is very simple to verify. Can imagine that. Okay, alpha x squared is just the alpha times with the x1 square, s2 square plus s3 square dot until n divided by n of it, then it becomes alpha, and this one is the bracket s squared. Okay, so okay, if you want to continue this one is equivalent to like s squared is what? S squared times with the certain thing. Okay, there's one point. Okay, you need to check that when we are talking about this one, we'll take any value with the equal probability, right? Okay. When this one, any value of x, it will take equal probability. Okay, it will becomes the Boltzmann function, Boltzmann distribution. What does it mean? It means that it is proportional. It means proportional to the Boltzmann factor. Okay, you can think this one as the probability density. Okay, probability density. And if you are encountering statistically, this one is probability density, right? And if this one is s is a continuous variable, so and we're encountering it when you are taking the mean, right? In this Boltzmann distribution, okay, Boltzmann distribution with the probability density is the e power something, negative power something. Okay, you need to like taking the integral of all the variable of x from, let's say this one, all of the variable of x is like negative infinity to infinity with dx. Okay, your s squared need to times with the probability density. Okay, so your weight, you need to check that why does it true? Okay, if you are curious, why does it? This one equal probability will link to the Boltzmann distribution. Okay, so and you need to divide it by the total of it. Total of it is like e negative infinity to infinity for the probability density. Okay. Okay. So we have two integrals that seems like very dangerous. Okay, but it's very useful. It's a very, it needs some step. Okay, beta. Notice that beta here is a constant. Alpha here is a constant, and actually beta here is um 1/kBt. It's a constant. Okay, for the fixed temperature. Okay, let us see about the two integral. The first integral is like the infinity to infinity x squared e of negative beta alpha x squared dx. Okay, this one how we can solve it. Okay. For example, maybe you can use like DI method. You separate it x, and for example x e negative beta alpha x squared dx. Sorry, DI method. You differentiate this one, you integrate this one. Different DI method is like the integrating. Sorry. Wait, sorry. So okay, this is okay DI method. Integration by part. Integration by part. DI method is a shortcut they are using. So you can separate this one, or I can introduce another technique. We call it as the Gaussian integral. In fact, in physics, right, you will encounter many times on the Gaussian integral, not only in kinetic theory. Okay, Gaussian integral is something like you have the integral of negative infinity to infinity, the exponent of negative a is a constant of x squared. Okay, the x it will give you the square root of pi over a. A is a constant again. Okay. Yeah, you can try to prove this. Why does it true? There is different method you can prove. For example, you can let that I square equal to negative infinity equal to infinity e negative a x squared dx. And I change the variable to y, negative infinity to infinity e negative a y squared dy. Okay, and this one become like negative infinity e negative a x squared plus y squared dx dy. It becomes a double integral. Okay. If you know that you can how to solve the double integral, you can change your variable. For example, x squared plus y squared, and let r squared equal to x squared plus y squared, and x equal to r cos r sine cos theta r sine theta. So our dx here is like the negative r sine theta dy r cos theta. Okay, but then this one, right, maybe you don't need this, but then you need to know that how you can change your dx dy becomes the r d theta, because you change your variable with r and theta, right? Okay, you change your variable. I mean, you change your you change your coordinate system. Just now is a Cartesian coordinate system, x and y. You change your coordinate system become r and theta. Okay, x and y. So you can change to r and theta. Okay, so it's like system, different system. So what is ds and dy? Let's say you have 2 points. Okay, this one is dx, this one is dy. Like this. Dx dy is what? Okay, let's say this one is dx, the length in dx, and this one is dy. So it becomes a dA. Okay, okay, dA. If you change your coordinate system, it becomes like, for example, you want to change your become r and theta. And dA here actually is a dx and dy. In the coordinate system, for example, this one, the area, Okay, let's say you have a center point. This one your central point. The origin. Okay, you link to here. Okay, and you'll get something like the area. If something like if you dr, all dr comes with dt. Okay, so you're changing your variable from the infinity to infinity. Okay, it will be the same. Dx, I'm sorry, dr d theta. So we are changing your dx dy to dr d theta, and you get something like dr theta. Okay, and there's a front thing. Okay, this one you continue with your double integral. Okay, okay, you can check on that. And yeah, so it's we get something like pi over a, and I is become square root pi over b. Okay, you need to know that this one I, we want to have I. Okay, yeah, at the end I will include how we can solve this because time issue. Okay, there's another method I can show you also. Okay, so let's say we have a okay, just now like e with a x squared dx is square root of pi over 8 Gaussian integral. Let's say you get this already, and you want to apply to your original equations. Okay, original equation is something like here and here. So yeah, so your denominator is equal to square root pi over 8. Okay, so this one is what? A is the beta alpha. Okay, beta alpha. Square root pi over 8. A is here. Beta alpha. And there's another one. So it's like the numerator. Numerator, let me write it again. Your numerator, you need to solve like x squared. Okay? And there is alpha here, so I skip it. The alpha. Yeah. So A here is a beta alpha. Why is how we can solve it? It's okay. We have this useful integral. Okay. This one we can have another trick. Okay. Let's say we define a function. Okay. If we define a function, our function is what? Is this integral. Okay. But then with the variable of a instead of the function, instead of the variable of x. Why we can do this? Yeah, I mean, why we want to do this? We will get something like, for example, if you differentiate the function with respect to a, with respect to a, you will get something like d over dA of the same thing, right? Okay. But then your differentiation you can put inside because your with respect this one your differentiation is with respect to a, and your integration is with respect to x, so it doesn't affect it. So you can put inside. Okay. I mean, if you rigorous, you can try to prove why we can put inside the differentiation inside the integration. Okay, so you can differentiate, and x squared you can pull aside. So because it's a constant with respect to a, okay, so you can differentiate e minus ax squared with respect to a. Okay, so because with respect to a, right, this one is a constant x squared. You can think of like a multivariable calculus. Okay, so this one you get negative x squared. Okay, e negative ax squared dx. Okay. Oh, sorry, I should do this. Sorry, I should do this. Fa is like this, and yeah, erase the. I change my definition of function is equal to the Gaussian integral. Okay, I need to get something like this. There's a x squared in front. Okay, so yeah, change the definition. Then yeah. So we don't have an x squared here. So famous mistake. Okay, so you get something like negative infinity e negative ax squared dx is equal to negative, so x squared negative di over dA. So di over dA is what? Okay, your di over dA is what? Oh, sorry, df over dA. df over dA. Yeah, let me check. Is it true for me? di dA. di dA. Okay. Yeah. Okay, so is this one f is a function of a. Okay, and our function is what? There's another form we calculate just now. Our function is a Gaussian integral, right? Is equal to square root pi over a. Okay, so you can differentiate with respect to a. You will get something like the negative pi over 2 a power 1 over 2 is a negative 1 over 2. Okay, so bring our power, and you should get something like negative square root pi over a. Oh, sorry. This one is negative 3. Okay. So means that your integral x squared negative infinity to infinity e power negative x squared dx is the square root pi over a. Negative negative cancel. Okay. So negative here, positive here. Okay. Negative 3 over 2. Okay. And this is another result you want to use. Okay. Okay, let me just go back here. Okay, we have 4 minutes. Okay. Okay, we so here, right? Yeah. So here we want to verify it as the, okay, this is our equation, and this one is the e again. Okay, okay, so here is the square root pi over 2. A is what? A is the beta alpha beta negative 3 over 2. Okay, we substitute a result. So over the, this one is a Gaussian integral square root pi. Okay, a is the negative half power, so it's the alpha beta negative half. So eventually you will get what? So okay, so we need to calculate. This one will be cancel. And we get a 1 over 2 outside. Alpha will be cancelled. 3 over 2 plus negative plus become negative 1 over 2. Oh, 1, negative 1. Okay, so yeah, it becomes like 1 over 2 beta, and it becomes like 1 over 2. Beta is KBT, so it becomes a KBT. Okay, yeah. Okay, to write up a result. Okay, what we done just now? Just now we done the points that we want to verify that for the assumption of a large number of particles, okay, a large number of particles, the particles, each of the particles having the energy of E depends on their position. Let's say position is S equal to 0, so their energy is equal to 0, and position S equal to 1, so their energy will become alpha, okay. And we also have an assumption that for each of the particle occupying this energy, this different amount of the energy, right? Okay, different amount of value of X means that different amount of value of E, okay, is the equal probability. And we have a result of like when we have an equal probability, and you need to verify why does it true. It is the Boltzmann distribution, and the Boltzmann distribution, the probability density is the Boltzmann factor. Okay, the exponent something this one, and we want to verify that the average energy. Okay, the average energy is just the average of alpha I squared, and we can pull out the alpha. Okay, so this one is we treat the continuous variable of the statistical distribution. So our statistical distribution is a Gaussian distribution. Okay, you want to find the average. It's a continuous variable for X. So it's about the SDPM term trading if you haven't covered about it. So it's something about the this continuous variable statistic. Okay, so S can be continuous. So at the end, we use the Gaussian integral, our trick here, to find the fraction here, and we'll get a result of like equal to half KBT. Okay, half KBT. So yeah, I mean, what does it means for us? This one half KBT, right? Half KBT is the something we want to use for each of the degree of freedom. For each degree of freedom, there's the average kinetic energy of half KBT. Okay, so at the end, we can use it for generalize it to different variable. Let's say for different variable of X, okay, is linked to the quadratic power. We can use it for the this theorem for the find the average kinetic energy. Yeah, in others you can try to get it for the example. Okay. Yeah, hope you guys can get the points that how you guys can learn something from these 2 hour lectures. If you had any question, you can feel free to ask me also. Okay, so our lecture until here. Maybe see you guys again if you don't have any questions. See, thank you everyone for joining. Let me stop the recording. Bye bye.